With the tension forces now evaluated, it is time to turn to a study of the forces that result due to flows through the ether. What we will eventually be concerned with is finding an equation of motion for the attached positive and negative ether. There are three possible flows that can occur within our two-component solid ether model that will affect the equation of motion of the attached positive ether. Free detached positive ether can flow through the attached ether. Free negative detached ether can flow through the attached ether. And the negative attached ether can flow a little bit into and through the attached positive ether. Each flow rate is easily stated as the density of what is flowing multiplied by its velocity relative to the attached positive ether. For the case of the negative detached ether, the flow rate is given by rho sub dn times the quantity v sub dn minus partial p with respect to t. Here, rho sub dn is the density of the negative detached ether, while v sub dn is the velocity of the negative detached ether, and the partial derivative of p with respect to t is the velocity of the attached positive ether. This gives us the relative velocity of the flow times the density of the flow. For the attached negative ether, it flows with a rate given by its density, which is rho sub 0 minus rho sub dn, times its relative velocity, which is the partial derivative of n with respect to t, minus the partial derivative of p with respect to t. Here we recall that the total density of the negative ether is given by the sum of the detached component plus the attached component, and therefore, since that has to be equal to the constant rho 0, the attached negative density is equal to rho 0 minus rho sub dn. And again we have the velocity of the negative attached ether being the partial derivative of n with respect to t, and the velocity of the attached positive ether being the partial derivative of p with respect to t. Lastly, the flow rate of the positive detached ether is given by rho sub dp times the velocity of the detached positive ether minus the velocity of the attached ether. At this point, mention must also be made that a more precise terminology would have used the total time derivative rather than the partial time derivative in the flow rate expressions. However, since it is assumed that ethereal motions are small, the partial derivative of the ethereal position vectors with respect to x, y, or z is small. For that reason, the partial derivative with respect to time is the first-order quantity in the expressions. The analysis here keeps only first-order terms in the small quantities, and then will let the region of analysis tend to 0 to arrive at our desired result, which is a common technique when using calculus to evaluate physical phenomena. Continuing in this approach, note that we can also drop terms involving the detached ether density multiplied by the flow velocity of the attached ether, since the detached density is much less than the nominal density, and the attached ether velocities are small compared to particle velocities. Therefore, we can drop the terms involving the partial of p with respect to t from the first expression, as well as the terms involving the density of the detached ether in the second expression, and the term involving the partial with respect to p from the third expression. Next, our analysis must recognize that the total force will be proportional to the volume of our cube, since the size of our analysis cube will determine the size of flows for any given density. We can then formulate the flow force as the volume of the cube multiplied by some arbitrary constant multiplied by the flows that we have defined. But we must take care to use the proper sign for the direction of the forces as determined by our flow force law that was postulated in an earlier section of this webinar. Recall that our postulate was that flowing positive ether would result in a force on positive ether that's in the same direction as the flow, while flowing negative ether would result in a force in the opposite direction as the flow. Hence, the force on an arbitrary cube of ether is given here as equation 6. I've highlighted the equation in red boxes as it will be used later in this work. Now that all of the forces acting on the positive attached ether have been identified and evaluated, we can go on to determine the equation of motion for the attached positive ether. To recall, the attached positive ether can be acted upon by flow forces due to flows of positive detached ether, negative detached ether, and negative attached ether. The attached positive ether can also be acted upon by the tension forces. These forces have been evaluated in the previous slides. We will now bring together all of the prior analysis to arrive at the equation of motion for the attached positive ether. Here we recall both the tension force and the flow force that will act on the positive attached ether. It will be assumed here that the velocity of the attached ether is small compared to the velocity of light, and hence the non-relativistic equation F equals ma will be used. Now the mass of a cube of ether is equal to its volume times its mass density, while the acceleration of the cube will be given as the second derivative of its position with respect to time. We can then set ma equal to the sum of the forces to give the expression here. Here I have simply brought down the tension force and the flow force from our previous analysis. We can then divide each side of the equation by delta x, delta y, delta z to arrive at the equation of motion for the attached positive ether as shown here. We will now manipulate the expression for the positive attached ether equation of motion. Here we first repeat the equation that was derived on the previous slide. We will then divide both sides of this equation by t0 to result in the second equation. Then we will multiply each side of the equation by -1 and take the Laplacian term over to the left-hand side, and then do a little bit of rearrangement of the terms. We can then define 1 over c squared as equal to the mass density divided by the tension constant, and define K2 divided by the tension constant as 4 pi a squared over c, leaving the equation of motion for the positive attached ether in the form given by equation 7. This is another important result that I've put red boxes around, and we will be using it in the remainder of this webinar. With the equation of motion for the attached positive ether now in hand, we can go on to evaluate the equation of motion for the attached negative ether. One equation from the previous slide is shown here. Our derivation of the equation of motion for the attached negative ether will follow the exact same steps as did our derivation for the attached positive ether. And hence we can just replace p by n by p, and t0 by t0 prime. This leads to the equations shown here. The first equation is simply the above equation with the designated replacements. As we did for the positive case, the second equation simply divides through by the tension constant. The third equation reverses the signs of all the terms, brings the Laplacian operator over to the left, and does a little bit of rearrangement. In this slide, we start by bringing over the last equation from the previous slide. We will now define 1 over c squared as the negative ethereal density divided by its tension constant, and K2 over the tension constant as minus 4 pi a squared over c. This leaves the equation of motion for the negative attached ether in the following form. I've again put red boxes around equation 8, as it's an important equation that we will be using later in this webinar. A few comments are worthy of mention at this point. Firstly, note that the second substitution has involved a minus sign, whereas when we had the positive case, we had a positive sign at this point. Therefore, we've assigned the tension in the negative ether to be the opposite of the tension defined for the positive ether. Since the sign has been switched for the tension, the sign has also been switched for the mass density. Therefore, the first substitution involves a replacement that has the mass density of the negative ether equal to the negative of the mass density of the positive ether. This makes the positive ether and the negative ether a true matter-antimatter pair, where the constants associated with each are the negative of the other.